So what I'm going to do now is present two separate, but in some sense slightly equivalent methods of dealing with this problem. And this is called the method of finite differences. And these two methods are in fact equivalent to one another. The first method will provide us with some very interesting geometric insights that were actually first observed when solving this problem without the calculus of variations. However, the second method will give us something that's a little bit more important for kind of moving forward in the course. So for the first method of finite differences, what we're going to do is fix a partition along the y-axis. So we're going to fix a whole bunch of y values between 0 and h. I'll call these y values y1, y2, y3, all the way up to yn. And graphically speaking, this looks like the following. It's going to look like y1, y2, y3, all the way up to yn. So we have n different fixed constant y values. And recall that the functional is this integral of f of x, y prime. And recall the definition of the integral from calculus 2. This is the limit of Riemann sums, or the limit as n goes to infinity, as delta x k goes to 0 of the summation from k equals 1 to n plus 1 of f of xk, yk, yk, p times delta xk, where delta xk is xk minus 1, and ykp here is an approximation to the derivative of the curve that we're doing this integral on, because we need to approximate this derivative at a sample point. And there are many ways of doing this, all of which, if the integral exists, are equivalent. However, we're going to choose yk to be the backwards difference at the point when we're summing from 1 to n here, which is going to be yk minus 1 over xk minus 1. There are many different ways of approximating the derivative. However, this backwards difference formula is going to be the nicest thing to use for kind of illustrating this method. Now, essentially what this is an approximation where, when we've used the backwards differences here, we're kind of approximating this curve with straight line segments, linear segments, the slope of which is exactly the slope of the line going from point to point. That's what this ykp or what ykb is when we use the backwards differences. Now, the idea behind the finite difference method here is, instead of considering the limit, which is the exact value of the integral, we're just going to consider this summation, the approximation. And what you want to do is think about what is this approximation exactly in terms of what it's a function of. We've fixed the values of yk, so those are all fixed constant values for a given value of n, but what's variable here is the x coordinate of this approximation. For instance, you could choose any given x1, x1, x2, x3, x4 for this approximation, and what we want to try and do is actually optimize, so minimize this approximation for any fixed value of n. in terms of how it depends on x1, x2, all the way up to xn, this summation now with no limit, we're not taking a limit, we're kind of stopping this limit procedure, and we're going to fix n, and just consider what we get when we fix the value of n. And when we do this, we have that this summation right here, it depends on only the x's. So this is a multivariable function phi of x1, x2, all the way up to xn. Which means that phi is a multivariable function of x1, x2, all the way up to xn, all of the possible x values that we can choose. And we know how to optimize multivariable functions from Calculus 4, or a multivariable calculus class. To find a critical point of a multivariable function, we know that that's going to happen at either a point where the partial derivatives do not exist, or where the partial derivatives are all simultaneously equal to 0. And we're just going to consider that second case where the partial derivatives are all 0. We're going to assume that phi is a nice enough function, and this means that all of the partial derivatives of phi, or the partial derivative of phi with respect to xj, has to be equal to 0 for all values of j equal to 1 all the way up to n. This is the condition that is going to happen at a critical point of this multivariable function. This multivariable function is an approximation of the integral that we're trying to minimize. So to take this partial derivative, remember that we're taking the partial derivative of a summation here. So the partial derivative of phi with respect to xj is the same thing as the summation of the partial derivative of every single individual term in this finite sum. Remembering our differentiation rules from multivariable calculus and from calculus 1, we first need to realize that f here is a function of xk. It's also a function of ykp, which is itself a function of yk. So we need to split this and think about the derivative of this term as well as the derivative of this term, because this delta xk also depends on all the x values. So the first things here, this will be the same thing as the xj derivative of f of xk yk ykp, whatever that is, times delta xk plus the function itself, f of xk yk ykp, times the j derivative, xj derivative of delta xk. And this is the product rule. Take the partial derivative of this first term. We remember that if we have a function g that depends on, say, x, y, and z, which also depends on x, we have to consider the chain of dependence of such a situation and use the multivariable chain rule. So for such a situation, we have that g depends on x, depends on y, and then it depends on z, which is also dependent on x. And to take the derivative, the partial derivative of such a composition, we need to consider the multivariable chain rule. So it's actually the sum of all of the paths of dependence, the derivative along each one of these paths. So the derivative of such a composition will be partial g partial x plus partial g partial z times the derivative of z with respect to x. Now, in this situation right here, we have something a little bit more complicated, but it's still the same exact idea. So using this, taking the derivative, we get, this is going to be the sum from k equals 1 to n plus 1 times the partial derivative of f with respect to xj, and this derivative right here is going to be fx, where the subscript here stands for partial derivative of capital X, or capital F, at xk, yk, ykp, that's this x derivative right here, plus the derivative of f with respect to its third component, which is y prime, at xk, yk, ykp, times the derivative of ykp with respect to xj, and all of this is times delta xk. And then we have to add to that this term right here. So just f of xk, yk, ykp times the xj partial derivative of delta xk. So this is looking fairly long. And in order to simplify things a little bit, we're going to remember what we're trying to do. We're trying to solve the Brachistochrone problem by optimizing this approximating function phi that approximates the integral that we're trying to minimize in the Brachistochrone problem. So in the Brachistochrone problem, the function f, capital F, does not depend on x, which means that this partial derivative right here is going to be 0. So we're going to apply this simplification right now to try and simplify and kind of help us with our equations, but keep in mind that we're making this simplification right now. So what we really need to do is figure out what this derivative is right here, the derivative of ykp with respect to xj, and the derivative of delta xk with respect to xj. The first one, or the second one, is a little bit easier to figure out. The derivative of delta xk with respect to xj is equal to the xj derivative of xk minus xk minus 1. And so this is only going to be non-zero if j is equal to k or j is equal to k minus 1. It's 0 if j is not equal to k or j is not equal to k minus 1. And if j is equal to k, it's 1. And it's negative 1 if j is equal to k minus 1. So this one is a very nice simplification. What this means essentially is that this summation, you're summing over all values of k, is really only going to reduce to two separate terms. One where j equals k and one where j equals k minus 1. The derivative with respect to xj of ykp is a little bit more complicated, but it's not that much more complicated, because you remember we're using the backwards difference method for ykp. This is yk minus 1 over xk minus 1. And so this is nothing but, when we take the derivative of it, derivative of ykp with respect to xj is going to be equal to the derivative of this function, where we have to use the chain rule. Remember, you can kind of express this if you want to, because the yk's are constant. We can just call this delta yk times delta xk to the negative 1. When we take the derivative of this with respect to xj, this is going to be delta yk, because it's constant, with respect to xj, times negative delta xk, negative delta xk to the negative 2 times the xj derivative of delta xk. This is just the chain rule applied to this expression right here. And this is very neat. It means that this is going to be negative delta yk over delta xk squared times derivative of delta xk with respect to xj, which we already have from before. We figured that this is exactly this piecewise function right here. So this is going to simplify to 0, because this is 0 if j is not equal to k or j is not equal to k minus 1. But if j is equal to k, this expression right here is equal to 1. So when j equals k, we have that this is just going to be negative delta yj over delta xj squared. And because of the fact that this is negative 1, delta derivative of delta xk with respect to xj is negative 1 when j equals k minus 1. That negative 1 multiplied by this negative 1 gives you positive. So this is going to be positive delta y, and k here will be j plus 1, delta y j plus 1 over delta x j plus 1 squared, just like before from this formula right here. This is when j is equal to k minus 1 or k equals j plus 1. So what's very neat here is that these two simplification formulas for these derivatives, this derivative right here and this derivative right here, are going to reduce this summation. We're summing over all values of k here, but this derivative and this derivative are 0 unless k equals j or k equals j plus 1. So really the only non-zero terms in this sum are those two terms for this expression and those two terms for this expression, which is very, very neat, and it simplifies to the following. This will be equal to just this term right here when j equals k, when j equals k minus 1. When j equals k, you have fy prime at xj, yj, yj, p times, and this is where things are, you get really nice, you have negative delta yj over delta xj squared, but you have this is delta xk, when j equals k, this is delta xj, so you just have negative delta yk over delta xk. And remember what this is the same thing as negative ykp. And then the other term here is when j equals k minus 1. That's the other non-zero term from this sum. So you have plus then fy prime of xj plus 1, yj plus 1, yj plus 1p times yj plus 1, delta yj plus 1 over delta xj plus 1 squared times delta xj plus 1. This just gives you delta yj plus 1 over delta xj plus 1, which is just yj plus 1p. Just like this is negative ykp, or sorry, it should be yjp. And for the second term, you have this will be plus f of xj equals k minus 1 here, or k equals j plus 1. So x j plus 1, y j plus 1, y j plus 1 p times the j derivative of delta xk is 1 when k equals j, and negative 1 when j equals k minus 1. So this will actually be, this value is negative, so times negative 1. This derivative here is negative when j equals k plus 1, and then plus f of xj, yj, yjp times positive 1 when this term is, when j equals k. So remember that this entire thing is being set equal to 0. It says equals 0 because if you remember what we're trying to do, we always want to go back to what we're doing. We're setting the all of the derivatives of this approximation equal to 0 to try and minimize this function phi as a function of all of these possible, these x values. In this equation, setting this entire thing equal to 0 can be rewritten in a very nice form. What we've shown here, if you take all of the j terms to one side of the equality, you have that f of x, j, yj, yjp minus fy prime of xj, yj, yjp times yjp has to be equal to f of xj plus 1, yj plus 1, yj plus 1p minus f of fy prime of xj plus 1, yj plus 1, yj plus 1p times yj plus 1p. And this is just taking this term on the same side, on the left side, this term is on the left side, and then adding this term to both sides and subtracting this term from both sides. So this is the fundamental relationship that we have has to hold if we want to maximize the approximating function phi for any functional of the form of the simplest variational problem. Now this is a really, really important result in and of itself. Geometrically it's very, very nice, especially for the Brachistochrone problem. If you go through and actually plug in the f and the fy prime for the Brachistochrone problem, you get a geometric relationship that has to hold between for the slopes of these lines, and that relates the slopes of these lines to the values x1 through xn and y1 through yn. Specifically, what we've shown here is that if these two things have to be equal to one another, we have the left-hand side is only dependent on j, the jth value in our approximation, and this has to always equal the j plus first value of this special combination of the function f. This is a very, very important thing because it's saying that the solution which optimizes this function phi for any value of n has a constant value of this expression. So this has to equal some constant c. And so let's look at what this means for the Brachistochrone problem. For this problem, our function f is really just a function of y and y prime. Specifically, it's the function square root of 1 plus y prime squared over the square root of 2gy, and that means that fy prime of y and y prime is going to be the y prime derivative of this, which by the multivariable chain rule, we end up getting that's y prime over the square root of 2gy times the square root of 1 plus y prime squared. And so we note that this needs to be true for all j. So for all j from 1 to n, which means that for any j, we can just plug in, and this combination will have to be the same constant. It's the identical constant that is shared by every single combination xj, yj, yjp for these two functions. So plugging in here gives us that this is going to be this term right here is the square root of 1 plus yjp squared over the square root of 2gyj minus fy prime, which is going to be yjp, because that's what we need to plug in here, over the square root of 2gyj times the square root of 1 plus yjp squared times yjp. This has to equal the constant c for all values of j. We can simplify this a little bit by bringing these two terms a common denominator, and when we do that, we get this first term is going to be 1 plus yjp squared minus the numerator in this term, which will be yjp times yjp, which is yjp squared. And when we bring it to common denominator, we have the square root of 2gyj times the square root of 1 plus yjp squared. This entire thing equals c, which is just the statement that 1 over the square root of yj times the square root of 1 plus yjp squared. 2g is a constant for any one of these problems, so we can just multiply it to get that this is equal to the square root of 2g times c, or we'll call it some new constant d. So for the Brachistochrone problem, we have that this combination, 1 over the square root of yj times square root of 1 plus yjp squared, has to be equal to a constant value. And this is very neat, because geometrically this is telling us something very nice. If you look at any one of these segments, say from the point xk minus 1, yk minus 1 to the point xk, yk, this straight line segment is forming a triangle, where the vertical of the triangle is delta yk, and the horizontal of the triangle is delta xk. And remember that ykp was chosen to be delta yk over delta xk. So what is 1 over the square root of 1 plus yjp squared? It's precisely the cosine of this angle, call it phi k, right here for any one of the segments, because the tangent of that angle phi k is exactly the opposite over the adjacent, which is delta yk over delta xk. So another way of rewriting this equation would just say that the cosine of this angle phi k, or phi j, over the square root of yj has to be this constant d. So geometrically, this is telling us something very, very neat, very, very nice about this problem. It's actually, this relationship is in some of the earlier proofs of the optimality of the Brachistochrone curve. This was actually one of the starting points of the derivation, which is very neat. So I'm going to change the color of these notes right here to yellow because these are reduced to the Brachistochrone problem, and this is what I did a little bit earlier when I kind of simplified for the Brachistochrone problem itself. So moving back to the general condition here that we derived, we want to solve the general calculus of variations problem, or finding the minimum value of this functional itself. And so if we've derived this condition that holds for all n, for any partition n of the form that we described earlier, it makes sense to now take the limit of this expression as n goes to infinity. And as this happens, as n goes to infinity, this condition right here reduces to the following condition. It reduces to a first order differential equation for the solution y. Specifically, it reduces to the condition f of y prime. Remember, we previously assumed that fx is 0, so f does not depend explicitly on x. So this f of y prime minus fy prime of y prime times y prime must be equal to this constant c. So in the limit as n goes to infinity, this condition that we derived earlier, this condition right here, reduces to this condition right here, which is in general, for the general problem posed before, the simplest variational problem is a differential equation that the function y must satisfy. If we consider what this means for the Brachistochrone problem, it essentially means that in the limit, this expression right here goes to 1 over the square root of y times the square root of 1 plus y prime squared being equal to the constant d. So if you plug in for f here, plug in for fy prime here, this is exactly what you're going to get in terms of what what this equation is for the Brachistochrone problem. If we consider that f specifically for the Brachistochrone problem, and this is a very special first order differential equation. It turns out that this is actually the differential equation of a curve known as a cycloid. And what I want to do right now is show you how we would get this by going through and determining the solution to this first order differential equation right here. Before I do this, I want to clarify a point here. Each one of for each one of the fixed values of n you could possibly take, so say 3 points, 4 points, 5 points, 100 points, it's going to necessitate that this constant right here is specific to that collection of n values. This c, because constant c here is going to be some cn. This will be cn and this will be dn. And the same thing holds for this equation right here. This is really kind of dependent on that fixed n, where n is the fixed number of points in our discretization. But so we'll call this cn, this dn, and then in the limit we'll just call the constant c, the constant that we get when we take the limit as n goes to infinity. So to solve the differential this differential equation right here for the Brachistochrone problem, what we want to do is remember what we noticed geometrically about this 1 over the square root of 1 plus yjp squared. In the limit, this yjp is going to go to the derivative at a specific point, the slope of the curve at a specific point. And so really, if for the discretization, tan of phi k is equal to delta yk over delta xk, in the limit, y prime is, this is a limit as n goes to infinity, y prime is going to be tangent of phi, and specifically what this means is that this 1 over the square root of 1 plus y prime squared is going to be cosine of this angle phi. So cosine of phi is going to be equal to 1 over the square root of 1 plus y prime squared. So this can also be written as cosine of phi over the square root of y. So it turns out that the better angle to use here, it's a little bit nicer to use here, is not this phi k, but this angle right here, which I'll call psi k. And in the limit, psi k becomes just psi of t. This is phi of t. The relationship between tangent of phi and the angle psi that you get in the limit is going to be exactly, you have here tangent of phi. This is the same thing as in terms of psi. Y prime is equal to cotangent of psi, because the angle psi is pi over 2 minus phi. So using some basic trigonometry, you can see that this clearly has to be the case. It turns out that to solve the Brachistochrone problem, to solve this differential equation, it's a little bit nicer to use this cotangent of psi, because this means then that if you look at the term that you have in the Brachistochrone problem, this differential equation, if we square both sides here, so this squared and this squared, we end up getting the differential equation 1 over y times 1 plus y prime squared is equal to d squared. And this means that this differential equation is the same thing as y times 1 plus y prime squared is equal to 1 over d squared, where we'll just call this the same thing as b squared, where b is some new constant, just so we don't have to write 1 over d squared every single time we write this down. Note also that 1 over 1 plus y prime squared with y prime equals cotangent of phi is the same thing as 1 over 1 plus cotangent of, oh, not phi, but psi squared, which is the same thing as sine squared of psi. So if we use this right here, this condition right here, that 1 over 1 plus y prime squared is equal to sine squared of psi, and we solve this equation right here for y, we obtain that y is equal to b squared over 1 plus y prime squared, which is the same thing as b squared times sine squared of psi. And this is going to be very useful, because if y equals b squared times sine squared of psi, we can take the derivative of this with respect to psi. So dy d psi is equal to b squared times the derivative of this expression with respect to psi, which is 2 times sine of phi times cosine of phi, psi, so this is one differential equation. And remember, we know how y relates to x. We have that y prime equals cotangent of psi. So this means that dy dx is equal to cotangent of psi, or by the inverse derivative theorem from calculus 1, the derivative of x with respect to y is going to be 1 over cotangent of psi, or this is just tangent of psi. And if we plug in this relationship right here, we use this relationship right here, this then means that dx d psi, when plugging that in right here, is going to be equal to just 2b squared times sine squared of psi. And if you're wondering where this is coming from, you can note that for parametric curves, if x is a function of psi and y is a function of psi, dx dy is going to be the same thing as dx d psi over dy d psi. We know that this has to equal tangent of psi, and we know what dy d psi is. It's exactly this function right here. So plugging in, solving for dx d psi will give us exactly 2b squared sine squared of psi. Recall that we can use the double angle identity on sine squared of psi here. So sine squared of psi is the same thing as 1 minus cosine of 2 psi over 2, which means this entire thing is just b squared times 1 minus cosine of 2 psi. And so this is a very nice system of differential equations that we can now solve for x and y. If we integrate the differential equation for x first, because that's the easier of these two differential equations, the antiderivative of 1 is psi, and the antiderivative of cosine of 2 psi is 1 over 2 times sine of 2 psi. So x, once we do this integral, is going to be equal to b squared times psi minus 1/2 sine of 2 psi, and the second antiderivative with respect to psi is a little bit more complicated, but it's not too bad. It's going to be done by a u substitution. You basically have the integral of sine of psi times cosine of psi d psi when you do this integral right here, and you do a u substitution of u equals sine of psi. So du is going to be equal to cosine of psi d psi, and this is going to be equal to u squared over 2 plus some constant of integration. When we go through and do this integral right here, and u here is the function sine, so it's sine squared of psi over 2 plus this constant of integration. Where again we can, to simplify what we're writing down, use the double angle formula. Sine squared is 1 minus cosine of 2 psi over 2, so this will be 1 minus cosine of 2 psi over 2 is over 4 plus e. And so when we plug this into this expression right here, after we do this integral right here, you have 2 times this entire thing, so it'll be 2 times this entire integral, which means that we get b squared times 1 minus cosine of 2 psi. We're dividing by 4 here. We have a 2 right here though, so we have b squared over 2, and then plus some constant of integration g, where this g is e times b squared. The constants don't really matter because they're determined by our initial and final conditions on this curve. So this is the exact solution to that differential equation parameterized by this angle psi. Now, if you go to, say, Wikipedia or some other source to look up the equation of a cycloid, this does not match what you see, but it can very easily be put into a matching form. Specifically, if you introduce the variable theta, where theta is equal to 2 times psi, this expression simplifies a lot. Psi will become theta over 2, and so you have x is equal to b squared over 2 times theta minus sine of theta, and y is equal to b squared over 2 times 1 minus cosine of theta, and this plus g. So this equation right here is exactly the correct equation that you'll see if you look up the equation of a cycloid. So this is it. This proves that the optimal solution to the Brachistochrone problem is a cycloid. Now, we haven't proven that it's a minimum, but that would take a little bit too long right now, and I'm not going to go through and show that, but rest assured that this is in fact the minimal solution. And oops, I just realized that I need another arbitrary constant of integration here. I'll call that f for the x integral as well. This is the most general solution, which is this is just a shifted cycloid, shifted to the point f at x0 and g at y0. And so if we switch to kind of get a visualization here, this GeoGebra applet is something that I created to visualize the curve that I just derived, with all of the constants solved for. So this is the general problem where you move around the point A comma A and the point B comma B here. You can move them to any point here that you want to and solve the problem, which is very neat. The only point of concern is actually solving for that coefficient b squared, or the coefficient that's being multiplied in the cycloid equation. So that b squared over 2 that shows up in the cycloid equations actually is the radius r of the circle that the cycloid is being constructed from. A cycloid is the curve that you get when you roll a circle along a straight line. So that this r right here is b squared over 2. But you can very clearly see that no matter where I move this endpoint to, we're always getting some cycloid that's directly determined by those previous equations that I wrote down being graphed right here. So this is very neat. What's interesting as well is that even if we take a step back and we go to the system of differential or the system of discrete equations that need to be satisfied, and we go through and try and solve this system, we can even see that the discrete system is converging to the cycloid. Now, there's going to be a little bit of an issue. And try and see if you can understand where that issue is coming from. So I wrote some Python code to visualize this. So we'll start here with 4 points. This n equals 4. And with 4 points, you see that we get, it's not a super nice discrete version. The exact solution is this cyan curve right here. But if we increase the number of points to n equals 5, we get a slightly better approximation. If we increase to n equals 6, it seems to be converging to the actual solution. So the numerical approximation here are these magenta points in the segments. This seems to be getting closer and closer and closer to the actual solution. That's what that was when n equals 7, and now we can do when n equals 9. This is getting closer and closer and closer to the actual curve. But at a certain point, we're going to see that this actually is going to break down. And it breaks down because of the infinite slope at the origin, or the initial point of the curve. The cycloid has an infinite slope at that point, at the left end point. And so because of that, this is really affecting the stability of this numeric system. So we have to be careful with this because this is definitely going to possibly not be very nice. The smaller we go with n, because we're getting closer and closer and closer to the point where the derivative is discontinuous. However, even for n equals 20, we get a fairly nice solution. And to be clear, that numeric code that I just presented is solving this equation right here. That this for yj has to be equal to this for j plus 1 for every value of j. However, a way around the problem that I just showed is to use this relationship instead, this geometric relationship, because this does not involve yj prime at all. It involves just cosine of the angle at every given point. So you could expect a little bit better behavior if you were to say take the code that I wrote and rewrite it to solve this system instead.